Okay, many of you asked for me to make a video about the material from weeks 8 and 9, counting principles. So these next questions are the ones from the quick review I made, so we'll go over those. All right, so first of all, building labels its offices with one capital letter, A through D, followed by an integer 10 through 30. So basically every office label is going to have a letter and a number. Remember, and in math corresponds to multiplying. So what we must decide is how many choices we have for the letters, how many choices we have for the numbers. So A through D, that's A, B, C, D. So we would have 4 choices for letters. And for numbers, you must be careful here. For the numbers, you might think, oh, the numbers 10 through 30 is, you would subtract, and you'd say, oh, that's 20 choices. But be careful. You actually have to add 1 to that because we're including both the endpoints, 30 and 10. So in fact, this is 21 different numbers. So just be careful there. If they say an integer from this range to that range, you subtract, but then you add 1 more just to make sure you're including both endpoints. So now we've got 4 letter choices for the first slot, and we've got 21 number choices for the second slot. So we multiply that, and we get a total number of 8 office labels, being 84 different office labels. Okay, let's do some more like that. How many different license plates are possible if the first 2 characters are an uppercase letter and the following 4 characters are digits? So again, we've got 2 letters followed by 4 digits. I would always advise you to draw a picture like this. So these are letters, and then we have digits. Digits just means a number between 0 and 10. So again, our license plates have to have all these spaces. So we need a first letter and a second letter and a first number and a second number, third number, and fourth number. So all of these are going to be multiplied together, and in math corresponds to multiplying. And we, piece by piece, look at how many choices we have for each space. So the first 2 characters are an uppercase letter. So that's 26 for the first, 26 choices, A through Z, 26 for the second letter, A through Z, and then the next 4 are the digits 0 through 9. So again, remember, you can't just subtract 9 minus 0. There's 9 minus 0 actually plus 1, so there's a total of 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. If you count all of those, that's 10 choices for each of these 4 slots. And when we multiply it all out, we get a very big number, which is 6,760,000 different possible license plate combinations. Okay, let's look at this next question. I think it gets a little bit more complicated here. You can choose either a 3 or 4 character password. Just remember, in math, or is plus. So our choices are 1, 2, 3, or 1, 2, 3, 4. Okay? So or corresponds to plus. Each character must be an uppercase letter or a digit, and we want to know how many different passwords are possible. So each time you can either choose one of 26 letters or a digit. So basically for each slot we have 36 choices. Now the first password, that's 3 characters long, would be, you have 36 choices for the first, and 36 choices for the second, and 36 choices for the third. Or you could have this many passwords. You could have a 4-digit password, so 36 choices times 36 times 36 times 36. We'd type in, this is 36 to the third, or this one would be 36 to the fourth. Let's see, when we plug that in our calculator, how many total choices we have for passwords. Turns out it's a very big number, 1,726,272 passwords that are either 3 characters long or 4 characters long. Okay, let's look at this one. We have 3 sections of students. We've got section A has 12 students, section B has 17 students, and section C has 8 students. How many ways can one student, only one student, so basically I'm saying I'm choosing one. I'm choosing one, right? So I can either choose from A or B or C. That's where I can choose from if I'm choosing one. Well, there's 12 choices from A, or corresponds to plus. There's 17 choices from B, and again, or corresponds to plus. There's 8 choices from C. So if I'm going to choose only one student, I'm choosing 12 plus 17. I'm choosing between 37 different students. So that's how many different ways I can make that choice. Okay, this is a similar type question. We've got a menu, and we've got appetizers, and there's a choice of 5 of them. And you've got entrees, that's the big menu item, and we've got a total of 7 entrees. So I go to the restaurant, and I'm only choosing one. I'm only choosing one item, okay? So if I'm only going to order one item, I either order an appetizer or an entree. And remember, in math, or corresponds to plus. So there's 5 different appetizers, 7 different entrees. So I have 12 ways, 12 options of how I can order just one item off that menu. All right, now we're talking about bit strings, which, as a reminder, this is a very CIS vocabulary word. Bit string means that each character is a 1 or a 0. And we've got 8-bit strings, 16-bit strings. In this case, they say it's a bit string of length 6. Okay? So it's going to be 1, 2, 3, 4, 5, 6. But here's what they're saying. How many of them either start with 1 or end with 0? Let me write this the math way. What we're asking is, what's the quantity? So we put these bars around it. It either starts with 1 or it ends with 0, 0. Okay? So when you have quantities to do with or, we can separate this out. Let me actually show you the general rule that I'm going to be working with. The quantity of A or B means you can say, well, it's the quantity associated with A plus the quantity associated with B minus anything that is duplicated. So if it's both A and B at the same time, we'll subtract that, so we're not counting twice. So in this case, we're saying how many of them start with 1, okay? And then how many of them end with 2 zeros? But we must subtract any that have both. So they both start with 1 and end with 2 zeros. So we actually need, I'm going to go ahead and erase this now just so I give myself some more room. We need to find out the number in each of these categories. So let's look at starting with 1. Okay, it's a bit string of length 6. 1, 2, 3, 4, 5, 6. Okay, if it starts with 1, then that's the only choice I have for that first slot. But for each other slot, it could be either a 1 or a 0. So I have 2 choices, 2 choices, 2 choices for each of these slots. Again, we're not putting the numbers that we can choose for the slots. We're putting how many choices do we have. So in order for this 6 character long bit string to exist, we have this choice of 2 to the 5th choices, which by the way is just 32. So there's 32 bit strings that will start with a 1. Let's look at ending with 00. So there's 6-bit string. And if they both end with a 00, that means there's only one choice and one choice for those last two. But for the other slots, they can start with anything. So I've got 2 choices, 2 choices, 2 choices. So it looks to me like the total number of bit strings that end with 00 is 2 to the 4th, which is 16. So in the end, let me erase these little equal signs. And in the end, we're going to have 32 plus 16 minus however many have both of those characteristics. So if it starts with a 1, 1, 2, 3, 4, 5, 6. If it starts with a 1 and ends with 00, it means for those spaces we don't have any choice at all. The only thing we have choices for are these middle spaces. Okay, so if I multiply all that together, that's 2 to the 3rd power, which is 8. So the number of characters that have those characteristics, the number that we've got, start with 1 or end with 00. It's 32 plus 16 minus 8, which is 40, I believe. Okay, this question is similar, but it's using a little more practical real-life examples. It says there's 250 employees, 160 of them like coffee, 100 like tea, and 70 employees like both coffee and tea. How many employees like neither coffee nor tea? Well, this question is going to take a few steps. So we would write this. How many like neither coffee nor tea? Let's first find how many do like coffee or tea. So coffee or tea. How many like coffee or tea? So according to the rule, we'll say it's the number that like coffee plus the number that like tea, but we will minus any that like both coffee and tea. So let's see those numbers. How many like coffee? It's 160. And 100 like tea, but there are 70 of them that are duplicates because they like both coffee and tea, so we'll subtract those. So the total number of employees who like coffee or tea is, looks like 190 employees. So 190 employees like coffee or tea. But that's actually not what they were asking. They're asking how many like neither. Well, these 190 like one or the other, or even both. So the way we figure out how many like neither, you'd say not liking coffee or tea. What you do is you take the total number of employees and you would subtract, well, how many do like coffee or tea? So in this case, the total is 250. 190 of them do like coffee or tea, so we are left with 60 do not like coffee nor tea. Okay, next question. How many different ways are there to arrange 8 colored beads on a necklace? Remember, these circular problems, we have to think about them slightly differently. Here we've got beads on a necklace, 8 of them this time. And I'll make it very pretty. I'm going to color them with 8 different colors. Okay, so we've got all the beads on a necklace. The first way you want to approach this problem is imagine that it really was just like a string of 8 beads. 1, 2, 3, 4, 5, 6, 7, 8. Okay, if it was a string of 8 beads, then the way you would do this calculation is you'd say, all right, the first bead, I have 8 colors to choose from. Then after I use that one, I have 7 to choose from, then 6, then 5, 4, 3, 2, and 1. The problem with this, there is a slight problem, which is because it's not a straight line, now that we've made it into a circle, we've connected both ends, there's really no beginning point and no ending point. And so it's actually going to remove some duplicate combinations. Because why? If this order right here in this picture was just shifted 1 unit to the right, it's still the same necklace with the beads in the same order. So every time we shift it 1 unit to the right, we're still going to get some duplicate orders of the colors of beads. So what we must do whenever we have a circle like this is we'll calculate all the different combinations as though it was a straight line, and then we will divide by the duplicates, which is actually just the number of turns, number of spaces we can rotate and have it still be the same order. So in this case, since there were 8 colored beads, there's 8 additional ways you can turn the necklace and have it still be the same order. So in fact, basically the 8 will cancel, and you get 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040 different color combinations for your necklace. Okay, the next 2 slides are the pigeonhole principle. Okay, we've got first this standard pigeonhole principle, which is basically like there's some number of categories, and we're going to pick things out of a pile and stick them in the right category. So in this particular example, we've got playing cards, and we're going to put them in categories of suits. If you remember, I like to draw the categories like boxes or buckets. So for playing cards, we have 4 different suits. You've got hearts, you've got diamonds, let me make this pretty, hearts, diamonds, and you've got spades, looks like that, and you've got clubs, which look like a little clover. Okay, so there's 4 different suits in playing cards, and the question is, what's the minimum number of cards you must choose to guarantee you have 2 cards of the same suit? So the idea with this is, first let's label a variable k. K is going to be the number of categories. So in this case, we have 4 different categories that when we pick a card, we'll have to put it into one of those categories. Okay? The second thing I want you to designate is the letter R, which is basically the number of successes. And when I define success, I mean choosing what they ask you to choose. So they say 2 cards of the same suit. So in this case, having 2 of a category that matches is what they consider a success. So the way I want you to visualize it is think, okay, if I go 1 less than success, so I'm getting super close to success but haven't arrived, so meaning I got 1 card in each category. Okay, I've picked 1 card in each category, so I haven't yet succeeded. I don't yet have 2 cards in the same category, but I have 1 in each category. The very next card that I choose, I have to put it somewhere. So let's say the next card I choose is a heart. Well, now I have the case that I did find 2 cards in the same category. So you can look, if those dots represent cards, we'd have to pick 5 cards in order to guarantee that we have 2 in the same category. And there's a math formula for this. So the minimum n that you would need is always just k r minus 1 plus 1. And let me explain what that's doing. It's saying, look, how many categories were there? There were 4 categories. Fill them all up to 1 less than success. Success was having 2 in each category, but we'll fill it up to 1 less than that. And then once it's all filled up, then if you just add 1 more, you've got to put it in one of those categories, and then you will succeed. So in this case, 4 times 2 minus 1, that's 4 times 1 plus 1, is also 5. Same as what we got from visualizing it. Okay, let's move on. We're doing the same pigeonhole principle, but this one is more generalized. When I say generalized, I mean the success is a bigger number than just 2. So generalized pigeonhole principle. So let's read the question. And it says 6 different types of candies in a bag. Okay, So it seems to me that the number of categories is 6. I don't know what the candies are. We'll call them A, B, C, D, E, F. Different kinds of candies. Okay, there's 6 different kinds. So I'm going to pick them one by one and put them in their correct category. And success is if we have at least 4. So what they're saying is the R, the success, is the number 4. Let me visualize it. I want to visualize getting very close to success, but not yet succeeding. So that would be 1 less than 4. If I had 3 of each type of candy that I've picked out, then I haven't yet succeeded because success is getting at least 4. But I've filled up every category so close, almost to succeeding, but just under. And then, okay, the very next one I choose, I'm going to have to put it somewhere. It's going to be some certain type of candy. And at that point, I will guarantee that I have at least 4 of that type. So you can look at this. You could count all those dots. It looks like 3 red dots times 6 categories is 18, and then I added 1 more. Looks like 19. But let's double check with the formula itself. The formula says the minimum N is you take K categories, you fill them all the way up to 1 less than success, and then you add 1 more item. So 6 times 4 minus 1 plus 1, that's 6 times 3 plus 1, 18 plus 1 is 19, which agrees with what we calculated just visually. So that is the generalized pigeonhole principle. Okay, hope this review helps. Good luck, everyone.